Sad.
Mechanics seems to torment you guys. It's good torment to have. Any questions? Yeah.
Can we just talk about the symmetry? There's a homework problem where you have an infinite slab
Yeah.
that has a certain height, and it goes the direction of the volume current.
What problem number is it?
5.15.
Page.
I have it 240.
240. Okay, problem number 15, yeah. A thick slab extending from z equals minus a to z and infinite in the xy direction carries a uniform current. Find the magnetic field as a function of z, both inside and outside the slab. Yeah.
So my question is,
Yeah.
there's obviously symmetry in this problem extending in both directions, but
Yeah.
to set up our loop,
Yeah.
how would you do like a right-hand rule for an infinite
So, yeah.
to set it up?
Right. So first of all, I mean, one way to do it is to brutally calculate, but we wouldn't want to do that. But the other thing to do, so this is where the charge is, right? I mean, sorry, the current is.
Yeah.
And the current is, maybe coming out like this.
Right.
So first of all, use the argument that the current is uniform in direction. So use, and what's the expression for B? This is a J. So the J version?
J cross script R hat.
U0, no, there's no I, over 4 pi d tau. Yeah. Not that we'll integrate this necessarily, but the direction of J for all posterity, it was Melissa who knocked the video camera. It works. You can check this video in 20 years from now and tell your kids this is what you did. Just an unruly student in class. No. So first of all, the direction of J is in the x direction. So you know that there's, I shouldn't be doing this, but Jx hat. This can only be done when the direction of current is uniform. Now, this has to be perpendicular to this x hat and script r hat, separation vector, unit separation vector. In particular, it has to be perpendicular to x. So already you know that B does not have an x component. Now it can only have a y component. Okay? So, y and z component. Then you decide whether, and I haven't thought this through fully, whether B would have a z component. This is not that different from an infinite plane in the xy axis. Yeah? So I suspect B would not have a z component, at least here. The question is, will B have a z component here? Well, in that case, it's easy to do. There are 3 loops you can take. but this might be tricky. So at least think about it. Now you know that there's no x component.
Yeah.
Yeah? So just noodle with it and see if you can get the y and z component. I think the inside part should be fairly straightforward.
Because that's a function of z, where you are in the.
Correct.
Because I mean that's what the problem is defined. It asks for find the magnetic field as a function of z both inside and outside the slab. So there has to be some kind of z dependence inside the slab, and then I'm guessing as you go outside the slab, it becomes. I mean, the current becomes defined because it's from negative a to a.
Yeah.
But inside it's a function of how much.
Yeah, but if I wonder if the z field is uniform because it's negative infinity to infinity.
Right.
But remember, there's no z component normal here. So, and we'll talk about this, the normal component of z is continuous. So, it may be that the z component vanishes, I don't know. Yeah? So think about it some more, and I'll also think about it, and let me know by Wednesday to work out the details.
Okay.
It'll be terrible if we have to just integrate. Now,
There has to be some kind of symmetry behind it, right? Because it's an infinite thing.
correct.
Um,
Yeah. See, the problem with such a loop, integrating in such a loop, is, first of all, this has to certainly cancel this off because there's no preferred point in this direction. So you don't let this vanish already. Yeah? And so then if the direction of these two are the same, then B times, but there's a current flowing out. So, yeah, so you can imagine there's no Y dependence,
yeah. Yeah.
yeah? Or even X dependence in the solution. There's only a Z dependence. So then I'm guessing B is equal to, perhaps a guess, huh? B in the Y hat
Because we said that the z terms will cancel.
You have to be careful inside to argue that. It's clear that the X term would cancel,
Yeah.
but we have to make sure that the Z term would cancel.
Yeah.
And this might help. Okay. I'll also think about it some more. Okay, good. Oh, right. So, see this expression, mu0 I over an I in general, it is J d tau. Yeah. For A, the potential, it is just R. Okay? This we got from a Poisson equation. And this required for this to, this came about because why? Del squared A was equal to minus mu naught J, correct? But this was only true if and what bothered me last time as well, if this had this expression, is this expression consistent with this? And the answer is yes, but let's see, divergence of A equals mu 0 over 4 pi divergence of j over this quantity d tau prime. Correct? And then we'll do a little trick. Mu 0 over 4 pi. This is with respect to x, y, and z. These are primes. So the divergence won't see this vector. So it becomes j dot gradient of 1 over r.
So the J prime,
Oh, I'm sorry?
when you took the J out.
J prime, yeah. Yeah? And then we've made this argument before that this can be written as minus just how symmetric this is in terms of prime and unprimed variable. J prime dot yeah? Now this can be, so what am I using here? Divergence of a function times a vector is equal to gradient of the function dotted with a plus f times divergence of a. That's why this term is 0, so I only get gradient. That's how I got the gradient. Then I replaced it with a negative. Yeah? Now I'm going to use divergence theorem once again. Recall divergence of J J over this is equal to divergence of J. It seems like a totally unnecessary substitution, but it's what will enable us yeah? I mean, again, I'm just rewriting this one more time, except with the prime variable. So now this term is exactly this term. So then I'm going to go back and substitute this minus that. So divergence of A equals mu 0 over 4 pi. Two terms. One is going to be minus integral. There's a minus here because of this minus. Divergence dot J prime over this dt prime minus, which becomes plus 1 over this thing, divergence of J prime dt prime. So far, it's just an algebraic shuffle. Yeah? Nothing very exciting. Now let's start doing physics. Now this expression is true only if J goes to infinity. But this guy is what? Using divergence theorem, this is the volume of all space, right? And you let it go to infinity. So this term goes to 0. Now this one, from the continuity equation, is, maybe I should say rho prime. But this is steady state. So in steady state, what do you have? 0. And therefore, as expected, this formula, which is valid only if j goes to 0 and infinitely far away, is consistent with the fact that A is divergence free.
I'm convinced.
The initial algebra is not very insightful. Just your divergence theorem, and we haven't seen it over December break, so you're recalling it as we do it. But there are two things. Using the divergence theorem, you get that this is on the boundary of all space, and j goes to 0. Again, we're not studying cosmology. At most, we're studying astrophysics. So if you have a stellar nebula or galaxies colliding infinitely far away from j, it's not infinitely far away from the galaxy or very large distances away from the galaxy. J is not just falling to 0, it is exactly 0. So outside of charges existing in the entire universe, that subject, which is cosmology, or ridiculously exaggerated problems of an infinite plane with charges, this is very easily 0. And this comes from the fact that we're still studying magnetostatics. You okay, Chip?
I don't know, sometimes the primes throw me off.
Primes refer to sources. So
then why is there a prime on the operator?
right, so let me, now that the answer is already there, let me clarify. See, A is a function of x, y, z. J is a source. If you're using spherical coordinate system, it might be r prime, theta prime, phi prime, but they're all primes. This guy. So when I do divergence of A, just by looking at what this is, divergence is what? Oh, sorry, not that. This operator, the del operator, is yeah? So this operator will never see this. If I put j over here, it doesn't, when I said j prime, I really mean j as a function of x prime, y prime, z prime. If I put any function of x prime, y prime, and z prime, because, listen, there are sources. This is a very important point. It's a very good question that you ask. So here is where the sources are. X prime, y prime, z prime. When you look at over here, A is a function of x, y, z. So if A is a function of x, y, z, and I'm taking the divergence of A, I'm taking the derivative of A in this area. You know, derivative, you have to do f of x plus f of x plus delta x. You may have to move around, right? You're moving around in this area. But if you move around in this area, none of these variables are changed. So if I do this vector acting on this j, I will always get 0. But then I'm relying on a trick. I'm relying on a trick that this guy, what is that? Let me write this in Cartesian notation. Right? Now, oh, sorry, this is the magnitude. So derivative 1 over r, 1 over r squared, I don't care. I just showed you with this example. The same argument works. So when I take the gradient of this guy, I won't get 0 because I have x, y, and z. I get something. I don't know. We could spend 15 minutes to do it, but I don't really care. But I'll tell you one thing I know. Look at the combination. So this is the same thing as now what could this mean? This is short for this is only true for this kind of functions. I mean, you can make it to the cube, but it's very symmetric. Yeah? If I take the derivative with respect to x, I'd get 2 times this times 1. If I take the derivative with respect to x prime, I get 2 times this times minus 1. And that minus comes all the way through. So that's why I'm doing the cheating. So it was originally with respect to the unprimed variable. The unprimed variable does not act on the primed variable. It only acts on this. But when it acts on this, I can choose which variable it is. And then I make it a primed variable. Then I massage it back again to terms I know. Yeah? So now that I've given you the explanation, go back to the notes, watch the video again, make sure you clarify. It is actually a good question. You should pin it down. Yeah. We have been using this technique, but it takes a while to. Takes, by the time it sinks in, you have to see it a few times, right? Yeah. I saw the ad for a restaurant somewhere. I forget the name of the restaurant. I think it was Fat Sam's. It says Fat Sam's, food, music, and good times. First time people look at it, go food, food everywhere. Food, music, all right, food and music. Third time, oh, and good times, then you go to Fat Sam's. So same thing over here, you just have to see it over and over. There has to be compelling reasons, right? Eventually, you hear it long enough, you'll believe anything. So that answered the previous question. I had a plan for today. Right. So, again, since I cannot draw an infinite solenoid, I'll always do this. So, B outside is what? 0. There's B inside. And B inside is mu 0 n I z hat. This is an example problem. This is example 512. And B equals del cross A. The question is, what is the A everywhere? All I need to do is find an A that satisfies this. There is no DA, right? And Griffith says, and I'm not quite sure I agree, he says, once we get the answer, all you have to do is take the curl, do you get B? But he says you can check to see if divergence of A is 0. If it works, then we have the answer. Okay, fine. But that's an extra requirement. That is a choice that we, given an A, you can find a new A if necessary where the divergence is 0. Right? So the divergence of 0 is not an important check for us at this point because we won't be using that other formula. We'll be using a trick. It so happens, I think, that divergence is 0, which I'll let you check, and in fact, let me know tomorrow. When I say tomorrow, I mean next time we meet. The trick here is to use A dot dl. Because you have B over here, we're going to see what happens because we're just, again, we're creatures of habit. We're just such a, all we know is the right-hand rule in this point. Yeah, we know that Stokes' theorem kind of thing. So A dot dl from Stokes' theorem is what? Del cross A dA. Yeah? Well, what is del cross A? And of course, we're going to go through circular loops. Yeah? So A has many components. If I go through a circular loop, only the phi component survives. So then we're going to go, fine. Phi component survives, that's fine. Let me do this integral. And now I'm inside the solenoid. And then I do A phi times 2 pi s. I use this about the symmetry axis. Yeah? Dot dl. If I go, it's a perfectly cylindrical solenoid. So if I go in a circular path, do I expect A phi to be dependent on the position? No. So there's no integration. It just becomes A, the magnitude of the vector field, times the circumference of the circle. That's equal to B is also constant. Mu 0 n I pi s squared. And so, what is A phi? Mu 0, pi cancels, n I s over 2. I don't recall this expression, so let me check. Yep, it is correct. Now look at what Griffiths does. So anyway, any questions so far?
This is for variable s, but the variable s still has to be inside.
Inside. This is for the potential completely inside. So I should make that okay, we'll do the outside part. Okay. Now, Griffiths does this, which is pretty neat. He says, well, this is all the A there is. Why? Because if I take the curl of this guy, I'm going to get this. Yeah, obviously I just use Stokes theorem. That's it. We're done. But he also says, well, knock yourselves out, take the divergence you will get. So check to see that now let's do when S is greater than R. Okay? I will get A phi times 2 pi S is equal to mu 0 Ni pi R squared. Because we can be out here, but the magnetic field stops with the radius of the cylinder. Here R, of course, is the radius of the cylinder, the cross-sectional radius. So if I do my math right, again, you know I'm going to make this a vector and say it has only a component. I get the pi's would cancel, mu 0 n I over 2 R squared over S phi hat. Again, let me check. Yep. And so we will have found the correct values. And now I can make it a little more clear. Yeah? Melissa, happy?
Continuity too.
Good continuity. Well, good point. I'm going to come to that. Very good. So, let me come to exactly that. Good catch. You know, when you guys ask questions, you guys actually ask good questions. So I don't feel like none of you guys are bad students, but I also feel like you guys could work a little bit more. Is that fair? Because the questions are solid. I'm not getting like pointless questions. It's meaningful where I have to clarify in detail. Okay. Let me draw up. What's that? So let me do a recall first, because first of all, a parallel. And how did we do this? Well, we said, what happens if you have constant rho in the xy plane, right? In the xy plane. Rho equals constant. Because if you have a complicated surface, make it that complicated. Yeah? If you have a complicated surface, if you look at a small patch of it and you zoom in, you'll find that it's a rectangular patch, much like the surface of the Earth. And then we argued that curl of E is 0, which means E dot dl is 0. Then we take a small, just a is that too small? No. I can exaggerate my perfect rectangular path. So what I'm doing here is zoom. And I have rho equals constant. And if I take a small rectangular path, half of it above, half of it below, and this is where the charge is, and I integrate this way. Yeah? I'm getting that this is 0. So this implies that the tangential component of E is 0, or I think we call it E parallel above minus E parallel below equals 0. But over here, divergence is not 0. So now I use divergence theorem and pick not a rectangle, but rather a box. And using this box, I conclude that E perpendicular above minus E perp below is sigma over epsilon naught. Because the total charge contained is sigma times dA. This rho, you're integrating over three-dimensional volume, but the charge is a delta function. It's a plane. Now, the magnetic field sort of a close cousin who despises you, just different in every way. If you diverge, they curl, and if you curl, they diverge. Yeah, and these are the two distinguishing factors. So, but charges don't create discontinuity. What creates discontinuity? Currents. And we did this problem because if you zoom again, any surface, you're going to get a flat surface, right? And the local discontinuity comes from this surface and not from far away. The electric field created by this charge at this point is discontinuous. The electric field created by this charge at this point, so if the charge is here, the electric field created here is continuous. Because if a charge is here, the electric field is continuous. But the electric field created by this charge over here, that's what creates this discontinuity. So these are very local properties, any discontinuity. Far enough away, fields are continuous. So again, if you have a surface with now a current, J, they can be thought of as this. We know the answer already. What was the answer? B was in a direction perpendicular to the x, Actually, this relates to Martin's question from the previous problem. So B was in the y direction. What did we get? B equals, there's obviously a mu.
Mu naught k over 2 y hat. Well, it depends on if the z is less than or greater than 0.
Right, so let's do this. B above.
B above is negative mu naught k over 2 y.
Negative mu naught k over 2 y hat. And B below, it's the same thing except and the reason being, you would go through a loop. Yeah? And when you're above the plane, you're going in the negative y direction to be consistent with Stokes' theorem. You might say, why go in the negative y direction? Well, I'll tell you why, because the current is coming out this way. You have to use the right-hand rule to be consistent. First of all, note that not only the normal component is continuous, it doesn't even appear. Not surprising. Here, the normal component appears. That's because the divergence is non-zero. Here, the divergence is 0. So, B normal above minus B below is 0. And then we have this fact. How can I write this vectorially? I will write it as B above minus B below U0 K. Because if I subtract these two, the 2's would vanish. So there's no over 2. Now I have to figure out direction. I know it's perpendicular to K. I want to get y-axis. Maybe I can even write this as k x hat, right? How do I get y-axis out of this? In fact, I should get a negative y-axis out of this. Cross it with z. Very good. X cross z is negative y hat. Correct? And then but that's terrible because it is x, y, and z, and this is a sheet in the xy plane. Normally, it could be in any direction, so I have to make this more geometric. And watch this. B above minus B below. I cheated a little bit. I used all the hard work done here just to translate it to this one. So read the argument with Griffiths. It's slightly different, but it's exactly the same in content. I'm giving you a little geometric meaning how this can be constructed. And so here it is, mu 0. This is nothing but, not j, but rather the k vector, k times x hat. And z is nothing but the normal. Correct? Normal what? Normal pointing above. There are two normals. One points above and one points below. So this guy In fact, that's what we mean by above in this equation. The direction n is pointing in. You pick the n you want, but whatever direction n is pointing in, we call it above. So we have this. We'll do applications of this. Before I box it so nicely, let me make sure it's correct. Yep. Any questions?